All right. Good morning, all. So we take another big step forward today, and get onto a new plane of understanding, if you will. So in the last week and a half, our focus was on the storage element or storage elements called resistors and rather inductors and capacitors. And resistors, or rather capacitors, stored charge, and inductors essentially stored energy in the field, the magnetic flux, and the state variable for an inductor was the current, while that for a capacitor was the capacitor voltage. We also looked at circuits containing a single storage element. We looked at RC circuits, and we also looked at circuits containing a single inductor, and these were inductors with a single inductor with a resistor and a current source or a voltage source and so on. So what we're going to do today is do what are called second order systems. So they are on the next plane now, and with these second order systems, they are characterized by circuits containing two independent storage elements. It could be an inductor and a capacitor, or two independent capacitors, and you'll see towards the end what I mean by two independent capacitors. So if I have two capacitors in parallel, they can be represented as a single equivalent capacitor, so that doesn't count. Okay, so it has to be two independent energy storage elements, and resistors and voltage sources and so on. And what we end up getting is what is called second order dynamics. Okay, and much as first order circuits were represented using first order differential equations, this kind you end up getting second order differential equations. So before we go into this, I'd like to start motivating this and give you one example of why this is important to study. Okay, there are many, many examples, but I'll give you one. So what I'd like to do is draw your attention to our good old inverter driving a second inverter, the same circuit that we used to motivate RC studies. Okay, one inverter driving another. Okay, so let me draw the circuit. Okay, so here is one inverter. This is, let's say, 5 volts, and this is, let's say, 2 kilo ohms. And I connect the output of this inverter to a second inverter. Okay? And what we saw in the last few lectures was that in this specific example, there was a parasitic capacitor or a capacitor associated with the gate of this MOSFET, and that could be modeled by sticking a capacitor CGS between the gate of the MOSFET and ground. And we saw that the waveforms here, if I had some kind of a step here, let's say, for example, a step that went from high to low, then out here I would have a transition that instead of going up rapidly like this, would transition a little bit more slowly. And this transition was characterized by an RC time constant, and this is what gave rise to a delay in the eventual output. So that's what we saw previously, single energy storage element. Today what we're going to do is we're going to look at the same circuit. Okay? The exact same circuit, and have some fun with it. What we're going to say is, look, this thing is pretty slow. Okay? So what I'd like to do is, why don't you go ahead and put that up? Okay, so what we're going to see is that the yellow waveform is the waveform at the input here. Okay? And this, the green waveform here is the waveform at this intermediate node. Okay? And notice that this waveform here is characterized by the slowly rising characteristics that's typical of an RC circuit. There's some other weirdnesses and so on going on here, like a little bump and stuff like that. You can ignore all of that for now. It happens because of certain other very subtle circuit effects that you won't be dealing with in called Miller effects and so on, that you won't be dealing with in 6002. So focus then on this part here. It's pretty slow, and because of that slow rising, okay, I get a very slow transition and I get some delay in my inverter. So you say, aha, we've learned about this in 6002. I can make it go faster. Okay, so how can you make the circuit go faster? What would you do? So this is rising very slowly. How can you make it go faster? Anybody? What are your multiple choices, actually? What are your choices here? Pardon? Decrease the time constant. And how would you decrease the time constant? The capacitance is connected to this MOSFET gate here. I didn't want it in the first place, but it's there. I can't help it. So I can decrease the resistance. Okay? Good. Let me go ahead and do that. So what I'll do is I'm going to knock this sucker out and stick in a new resistance that's, say, 50 ohms, a much smaller resistance. Okay? That should speed things up, right? That should make things go much faster because this is a smaller time constant because R is smaller. Correct? Okay, let's go do it. And let's see if we get what we expect. So I have a little switch here. And using that switch, I'm going to switch in this little resistance. Whoa. What on earth is happening out there? Okay? This is so much fun. So what I did is I switched in a small resistor here to decrease the time constant, but looks like I got a whole bunch of crapola that I did not bargain for. Okay, so this is certainly very fast. It goes up really fast. Okay, but I just can't, I'm not sure where it's going though. Okay, let's stare at that a little while longer. Let me expand the time scale for you. Okay, look at this. It's a nice little smooth thing going up. I get something that looks like this. It looks like it's something like a sinusoid. Okay, it looks sinusoidal, but then it's a sinusoid that kind of gives up and kind of gets tired and kind of goes away, right? Zzz, it kind of dies out. I mean, so nothing that you've learned so far has prepared you for this. Okay, and trust me, when I first got into, did some circuit designs myself a long, long time ago, I got nailed by that. I looked at my circuit, and what ended up happening was I was noticing these sharp lines at all my transitions. Okay, when I looked at my scope, I expected to see nice little square waves, but I saw these nasty spikes sitting out there. And then when I stared at it more carefully, those spikes are really sinusoids that seem to kind of get tired and kind of go away. So those are nasty, those are real, and they happen all the time. Okay? And what we'll do today is try to get into that and understand why that's the case. We'll understand how to design that away. And that's a real problem, by the way. And the reason that's a real problem is the following. Okay, look at this. Look down here. So because this intermediate voltage is meandering all over the countryside here, at this particular point, the intermediate voltage dips quite low. And because it dips quite low, look at the output. The output has a bump here. And it's quite possible for this output bump to now go into the forbidden region. Or worse, if this swing here was higher, this could have actually gone on to a 1. So I would have gotten a false 1 pulse here. So instead of having a nice 1 to 0 transition, I would have gotten 1 to 0, oh, back to 1, oh, back to 0, and then back down to 0. Okay, so this is nasty stuff, really, really nasty stuff. Okay, so what we'll do is understand why that's the case today and see if we can explain it. So what's going on here? What's really going on here is, take a look at this circuit here. But take a look at this path here, okay? And so this is your Vs voltage source. So the path kind of goes like this and around. Okay, turns out that this circuit is a loop here, okay? And when there is current flow, going down to basic physics, you remember that I also enclose some amount, so there's a current flowing in a loop, okay? And because of that, there is an effective inductance here. And in fact, any current flowing through a wire above a ground plane, for that matter, can be characterized by an inductance. Okay, so I can model that by sticking a little inductor here. So my real circuit is not exactly a resistor and a capacitor, but my real circuit is an inductor as well that comes into play because of this wire. Every wire, when there's a current flow, has an inductance associated with it. And because of that, the real circuit is resistor, inductor, and capacitor. Okay, so I end up with two storage elements now. And the dynamics of that are very different from that with a single storage element. Okay, so that's just a bit of motivation for why our study of inductors is important. Okay, and I can draw a quick circuit here. If you look at the circuit, start from ground, the voltage Vs, and there is a resistor here, okay, and then I have an inductor, and then I have a capacitor. Okay, so it's a voltage source, resistor, inductor, and capacitor. So for this whole week, we will be looking at circuits like this. Today what I'd like to do is begin, start very simple. Okay, so start with the simplest possible form of this to begin, so that you can begin building up your insight and then go into more complicated cases. So today what I'll do is simply begin with a case where I don't have a resistor here, and simply study a voltage source, an inductor, and a capacitor, and understand what the voltage looks like out here. Okay, so we'll look at the dynamics of a little system like this. Before we go on, I want to caution you about something. That it just happenstance that I have introduced for you capacitors based on a parasitic capacitance here, and inductance based on parasitic inductance. Okay, so I'd hate to leave you with the impression that inductors and capacitors are bad. Okay, because when you think of parasitics, parasites, these are parasitic, didn't expect them there, didn't expect us here. And I got the weird behavior. So parasitics are, they have a bad connotation to them. I don't want to leave you with a bad taste in your mouth about capacitors and inductors, that these are just bad things. We just have to deal with them and deal with second order differential equations and all that stuff because, they're just bad stuff. And we just have to deal with them. So I don't want you to end up going through life hating capacitors and inductors. Okay, just because of my choice of examples, it just happened to be introducing them as capacitors. Okay, I want to point out that these are fundamental lumped elements in their own right. Okay, they're very incredibly important and useful circuits where we design capacitors and inductors because we want to have them in there. Okay, there are many circuits that we will look at where we really want the inductor in there. We will design an inductor by wrapping wire around a coil, in a coil, and get bigger inductances and so on. Okay, so just remember that this can be parasitic in some cases, but in many cases it's good. Okay, inductors are good. Okay, so just stick with that thought. These are mostly good. Okay, so don't go around hating them. All right. So let's go on and analyze a basic circuit like this. And what I'd like to cover in the next hour are the foundations of something like that. Okay, I'll take you through the foundations so you understand how it works. And as always, what I'm going to end up with is build up the foundations, okay, help you understand why we got where we were, and then help you build intuition. And then show you a really, really simple, intuitive way of doing things in terms of how experts do it. Okay, and the real cool thing about EECS is that the way experts do things are really, really very simple in the end. Okay, but you need to build up some intuition to get there. Okay, so let's So our circuit looks like this in terms of my two storage elements. So I have a voltage VI, inductor L, a capacitor C, and I'm going to look at the voltage across the capacitor and my current through the capacitor. Okay, so V of t is the voltage across the capacitor, and my current is the current through this loop here, and which is the same as the current through the capacitor or the current through the inductor. Okay, and we're going to proceed in exactly the same manner as we did for first order differential equations. Write the equations down and just boom, 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 go down the same sets of steps, but just get to someplace different. So we're going to start by writing node equation for this node here. That's the only node for which I have an unknown voltage. The node here is VI. So I need to find this. There's just one unknown node voltage. And I'm going to need some element laws. So for the capacitor, I know the IV relation is given by, the I for the capacitor is C dV dt. And just to show a capacitor, I'm just calling it dVc dt. Similarly, for an inductor, L, the voltage across the inductor is given by L di dt. Okay, so this is the VI relation for the capacitor, the VI relation for an inductor. It also suits us to write this in an integral form. So if I integrate both sides of this equation, then what I end up getting, and I bring L down to this side, I end up getting something like this. 1 by L minus infinity to t VL dt, and that's simply IL. Okay, I'm just simply replacing this with an integral form. And so this is a VI relationship for the inductor, and this is for the capacitor. Okay, so let me now go ahead and apply the node method for my circuit here. So here, for the node method, I have to equate the currents coming into the node, or sum the currents coming into the node and equate that to 0. And while I do that, I simply replace the currents by the corresponding voltages using the element laws. So what do I get? So I get the current going in here through the inductor is equal to the current going through the capacitor. Okay? What's the current going through the capacitor? It's, in terms of its V relationship, it's C dV dt. So it's C dV dt. And the current going through the inductor is given by this relation here, which is simply 1 by L minus infinity to t. The voltage across the capacitor, that is simply VI minus V dt. Okay, so I've just written down the node equation for this node here. And now I'll just apply a bit of math and simplify it and get the resulting equation. So what I can do is simply differentiate with respect to t here and get this to be C, okay, the second derivative of V. And here, what I end up getting is 1 by L VI minus V. Okay? So I just differentiated the whole thing by d by dt here. And then I just shuffle and bring, rather I move L up here. I bring d squared V by dt squared out here. And then I get a minus V here. And that will be equal to, I'm sorry. Let me leave this here. Bring the minus V to this side so it becomes a plus. And leave VI on this side. Okay? So I end up getting LC d squared V by dt squared. I bring L up here. And then I take V to the other side, plus V, and leave VI here. So I get VI. The second order differential equation that governs the characteristics of the voltage V. So much as the voltage across the capacitor was a state variable in our RC circuits, or the current through the inductor was a state variable in our RL circuits, out here, both the current through the inductor and the voltage through the capacitor, voltage across the capacitor are my two-state variables. Okay, and so here I have a second-order equation in my voltage V. So again, going through the foundations here, I'm now going to go through a bunch of math. So up to here, it was circuit analysis, and now I'm just going to do math. Okay, for the next 3 or 4 blackboards, just math. You can solve this second-order differential equation any which way you want. Okay, but just to keep things as simple as possible, in 6002, I solve all the differential equations. It turns out we're fortunate enough we can do that using the exact same method again and again and again. Okay, the same thing can be applied. And the method that we use to solve it is a method of homogeneous and particular solutions. So as a first step, we're going to find the particular solution, Vp. Second step, we find the homogeneous solution, Vh. As a third step, we are going to find the total solution as the sum of the V is simply the particular plus the homogeneous solution, and then solve for constants based on the initial conditions and the applied voltage. So let's write down initial conditions. So let's assume for simplicity that my initial conditions are simply the voltage across the capacitor is 0 to begin, and the current through my inductor is also 0 as I begin life. Now, this is what is called zero state. V and I are both 0, and so the response of my circuit, okay, for some input is going to be called ZSR. You probably heard this term used in one of your recitations. So zero state response simply says, I start with my circuit at rest and look at how it behaves for some given input. Okay, so that it's a little term that you may end up using. My input next. I'm going to use the following input. So Vi of t is going to be a step. It's going to look like this. So my input is that at time t equals 0, okay, V is going from 0 to some voltage Vi and then stay at that voltage. Okay, it's going to be a step. Kaboom. Okay, and you can see why I'm going with this set of variables, because I want to make the situation as close as possible to the funny behavior we observed there. Remember, we had a step, and because of the step, we had some behavior at that node. Okay, so I'll try to bring you as close to that. And in tomorrow's lecture, I'm going to close the loop around that and derive for you exactly the behavior we saw on the scope. Okay, and to get there, I'm going to try to be as close as possible to the constants and other parameters in the demo. So Vi is a step, and zero state. Just in terms of notation, this kind of a step input occurs pretty frequently, and we just have a special notation for it. So we simply call it Vi is the final value here, and we call it U of t. So Vi U of t simply represents a step at time t equal to 0, where the steps from 0 volts to Vi. Okay, that's just a little more notation. That will come in handy at some point. Okay, so more math now. 3 steps: particular solution, homogeneous solution, total solution, constants. Okay, it's almost like a mantra here, like a chorus. Homogeneous solution we compute using a 4-step method. Okay, and 4-step method for homogeneous solutions, it turns out it happens to be that way for all the equations we'll see in our course. The first step would be assume a solution of the form A e raised to st, exactly as with RCs. You close your eyes and do exactly what you did for RCs, you'll get to where you want to be. So you assume a solution of the form A e to the st, obtain the characteristic, substitute that into your homogeneous equation, obtain the characteristic equation, solve for the roots, and then write down your homogeneous solution. Okay? Same set of steps again and again and again until you get bored to tears. Okay. So particular solution. So the particular solution, I simply need to find a solution, any solution, not the most general one, but any solution that satisfies the particular equation, which satisfies that equation. So LC d squared Vp dt squared plus Vp equals Vi. Okay, my input's a step, and I'm going to look for the solution for time t greater than 0. Notice that for time t less than or equal to 0, Vi or V is going to be 0. Okay, so I'm looking for a solution greater than t equals 0. So here, if I substitute Vp equals Vi, that is a particular solution, because if I substitute Vi here, this goes to 0, and then I get Vi equals Vi, so this works. Okay, I promised you this was going to be simple. Can't get any simpler than that. Okay, so I've done my first step. I found the particular solution, and Vi is a good enough particular solution, so I'll use it. I'll take it. So as my second step, I'm going to find VH, or the solution to the homogeneous equation. And the homogeneous equation is simply that equation with the drive set to 0. So what I get here is LC so that is my homogeneous equation. I simply set the drive to be 0. And to find the solution here, I go through my 4-step method. And again, in 6002, following kind of the Occam's, Occam's principle, we'll just show you the absolute minimum necessary to get to where you want. Okay, the absolute minimum necessary is that it turns out that we can solve all our differential equations that we use here by using the method of homogeneous and particular solutions. And every homogeneous solution can be solved by a 4-step method. I mean, that's about as minimal as it can get. Okay, so no extraneous stuff there. Okay, so the 4-step method. 4 steps. Okay, the first step is assume a solution of the form Vh e to the st. Oh, I'm sorry, A e to the st. Now, what I've noticed is that students starting out are usually scared of differential equations. Okay, I know I was when I was a student. Okay, and the trick with differential equations is that it's all a matter of psych. Okay, just because you see some squigglies and squirglies and a bunch of math and so on, you say, oh, that must be hard. But differential equations are actually the simplest thing there is, because in a large majority of cases, the way you solve them is you assume you know the answer. Okay, someone tells you the answer. Okay, and then all you're left to do is, shove the answer into the form of the equation and find out the constants that makes it the answer. Okay, so it's just a matter of psych. Psych yourselves that this stuff is easy. Okay, because I'm telling you what the solution is. Okay, all you have to do is substitute and verify. I mean, and when you think of differential equations that way, or a large majority of them, it really is very simple if you can just get past the squigglies here. Okay, just get past the squigglies and then just simply stick in some simple stuff, and it works. We just can't get any easier. I don't think of any other field where, the way you find a solution is assume you know the solution and stick it in. It's never made any sense to me, but that's how it is. Okay, so we assume a solution of the form A e to the st. We stick it in there, and we have to find out the A and S that make it so. Okay, I mean, can't get any simpler than that. So let's stick the sucker in here and see what we can get. So substituting A e to the st here, I get LC A, and second derivative, so it's S squared e to the st. Okay, and A e to the st for this one here, and that equals 0. Okay, and then let me just solve for whatever I can find. So assuming I don't take the trivial case A equals 0, I cancel these guys out. And what I'm left with is simply LCS squared plus 1 equals 0. Okay? In other words, what I end up getting is B S squared is equal to minus 1 divided by LC. So my first step was, I'm giving you a solution, stick it in there. assume a solution of this form. Second step is get the characteristic equation. And the way you get the characteristic equation is that you simply stick this guy in there, and what you end up getting is some equation in S squared, or for first order circuits. Do you remember what you got for first order circuits? What was it? S was? What is S? For first order circuits, what did you get as a characteristic equation? S plus 1 divided by RC equals 0. Okay, same thing. Just remember, just blindly apply the steps, and it'll lead you to the answer. So this is called the characteristic equation. Okay, this is incredibly important. Okay, you will see in about a couple weeks from now that once you write the characteristic equation down for a circuit, okay, it tells you all there is to know about the circuit. Okay, and oftentimes you can stop solving right here. Okay, to experienced circuit designers, this tells me everything there is to know. This is really key. That's why it's called the characteristic equation. Okay, I believe in problem number 3 of the homework that will be coming out this week. That's exactly what you're going to do. We're going to give you a circuit, ask you to get to the characteristic equation quickly, and then from there intuit the solution. Okay, write the cat equation, and then just intuit the solution. It's that simple. Okay, so step A, assume a solution of the form. Step B, write the characteristic equation down. Okay, and let me just simplify that a little bit. So I go ahead and find my roots, and my roots here, remember that J is the square root of minus 1. And so what I end up getting is, okay, so my two roots here are plus J square root of 1 by LC and minus J square root of 1 by LC. Okay, two roots. And just as a shorthand notation, much like I had a shorthand notation for RC, what was my shorthand notation for RC? Tau. Okay, just as tau was big in first order. Okay, we have a corresponding thing that's big in second order. Okay, and that's omega naught. Omega naught is simply 1 by square root of LC. Okay, just as tau was RC, omega naught is a shorthand here, and so S is simply plus or minus J omega naught. Okay, so notice that in this equation here, LC has units of, LC has, excuse me, if you take the square root of LC there, that has units of time. So 1 divided by that has units of frequency. Okay, so notice that this guy is a frequency in radians. Okay, so I end up getting my roots of the homogeneous equation, and that's my third step. And as my fourth step, I simply write down the homogeneous solution as substituting S with its roots and writing the most general possible form of the solution, and that would be A1 e to the j omega naught t plus A2 e to the minus j omega naught t. Done. Okay? Some constant times the solution plus some other constant times the other solution. Okay? Plus j omega naught. Remember, it comes from here, a to the st. I assume the solution of this form. So my solution in this most general case would be S being j omega naught in one case, minus j omega naught in the other case, and I sum the two to get the most general solution. Okay, so blasting ahead, I now have my homogeneous solution. And as my third step of solution to differential equations, I write down the total solution. V is simply VH plus, let me just do it this way, particular plus the homogeneous solutions. And V is, VI was my particular solution. And A1 e to the j omega naught t plus A2 e to the minus j omega naught t is my complete solution. Okay. So the final step, write down the total solution and find the constants from the initial conditions. So to find the constants from the initial conditions, let's start with the voltage is 0 to begin with. So this equation governs the characteristics of V. So I need to find the initial conditions. So first of all, I know that V of 0 equals 0. So from there, I substitute t equal to 0. And so this goes to 1, this goes to 1. I end up getting 0 equals Vi plus A1 plus A2. That's my first expression. And then I'm also given that I of 0 is 0. And so I can get that as well. How do I get I? So this is V. I know I is C dV dt. So I know that I is C dV dt. So I can get I by simply multiplying by C and differentiating this with respect to t. So I get C. This guy vanishes. So I get d by dt of this. So it's C A1 j omega naught e to the j omega naught t plus C A2 minus j omega naught e to the minus j omega naught t. Okay? And so from here, I'm given that that is 0. And so therefore, this guy becomes a 1. This guy becomes a 1. J omega naught cancel out. So what I end up getting is A1 equals A2. So from the second initial condition, I get A1 equals A2. So from these two, if I substitute here for A2, I get Vi plus 2A1 equals 0, or A1 is simply minus Vi divided by 2. And that is also equal to A2. Okay? So therefore, my total solution now can be written in terms of the actual values of the constants I have obtained. I get Vi minus Vi divided by 2. So A1 and A2 are equal. So I just pull them outside. So I pull Vi minus 2 outside. And I stick these two guys in parentheses here. Okay? Again, I promised you no more circuits from here on till the very last board or something like that. It's all math, so you know, not much else happening there. Okay? More math. Okay, if you like, I can skip all the way to the end and show you the answer, but let me just, you know, I just love to write equations on the board, right? So let me just go through that. So I'm going to simplify this a little further here. Okay? And we should remember this, this form by the Euler relation. E to the j x is cosine of x plus j sine of x. Okay, and by the same token, e to the jx plus e to the minus jx divided by 2 is simply cosine of x. Okay, you all should know this from the Euler relation. And so by using this guy here, e to the jx minus plus e to the minus jx is 2 cosine of x. Okay, and so the 2 and so this one is 2 cosine of omega naught t. 2 and 2 cancel out, and what I'm left with is v of t is vi minus vi cosine of omega naught t. And the current is C dV dt, which is simply C times vi sine omega naught t. And just remember that omega naught is square root of 1 divided by LC. We're done. Actually, I did not give that answer the importance that was due. So let me just draw. There, that's better. Okay, enough math. So let me just, in a nutshell, what did we do? We wrote the node method, did some very simple circuits to write down the equation governing that circuit. And then we grunched through a bunch of math, not a whole lot here, it's pretty simple, and ended up with a relation that says the voltage across the capacitor for a step input, assuming zero state, is a constant VI minus VI cosine omega t. So notice that even though I have a step input, the circuit dynamics are such that I get a cosine in there. Like you can begin to see where these cosines are coming from now. They're coming here. And if you recall the example I showed you earlier of the inverter circuit, remember it was a cosine that decayed, that was sort of losing energy and kind of dying out? So you can see where the cosines are coming from. And just to draw you a little sketch here, let me draw V and I for you. And let me plot omega t. So pi by 2, pi, and so on. Okay, let me plot VI and so when time t equal to 0, VI is 0, cosine omega t is 1, and so VI minus VI is 0. So that is simply a cosine of, it starts out at 0 here, and at pi, okay, at pi, I get cosine omega t is minus 1. Okay, so I get plus VI on the other side, so end up at plus 2 VI. Okay, so at this point, the voltage is here, and notice that this guy looks like this. Okay, it's a cosine that is translated up so that its mean value is not 0, but VI. It's just a translation up of a cosine. Similarly, in this case, for the current, it's a sinusoidal characteristic, and it looks like something like this, where the peak is given by CVI. Oh, I messed up. So when I differentiated this, I missed the omega naught out there. Okay, so what I'd like to do now, so this is the form of the output for a step input. What I'd like to do next is show you a demo. But before I show you a demo, I always found it strange that, I have a step input and then I have two little elements. How can I get a sign coming out of the output? Okay, I always like to get some intuition as to why do things behave the way they are. Okay, I could go and pray and try to get, to find out. But let me give you some very basic insight as to why this behaves the way it does. So let me draw the circuit for you here. Okay, and this is my inductor L and capacitance C. And remember, this is V. Okay, let me just walk you through what's happening there and get you to understand this. Now, you've seen signs occur before. If you go and write down the equation of motion of a pendulum, okay, you have a pendulum, you move it to one side, let go. Okay, it is also governed by sinusoidal characteristics, and you will find that the equation governing its motion is very much of the same form. Okay, and you get the sinusoid where you have energy that is sloshing back and forth between maximum potential energy to maximum kinetic energy and zero potential energy, back to maximum potential energy, zero kinetic. Okay, so it's energy sloshing back and forth. Same way here, capacitors and inductors store energy. And let's walk through and see what happens. So I start off with both of them having the states zero, zero current, zero voltage. So apply a step here. Boom, the step comes instantaneously to VI. And notice that the capacitor voltage cannot change instantly, unless there's an infinite pulse of a sort. So this guy cannot change instantly. And so its voltage starts off being zero. Okay, so the entire voltage here, KVL must be true no matter what. Okay, the absolute fundamental principles from Maxwell's equations. So KVL must hold, which means that the entire voltage VI must appear across the inductor. So I put a big voltage across the inductor, its current begins to build up. There you go. So a voltage across the inductor, its current begins to build up. As its current begins to build up, that current must flow through the capacitor too. And as current flows through a capacitor, it is depositing charge into the capacitor. So the capacitor begins to get charge deposited on it, its voltage begins to rise. Okay, so let's see what happens here. So its voltage keeps rising. At some point, the voltage across the capacitor is equal to VI. But then VI equals this VI here. So when the two become VI, the inductor has 0 volts across it. Okay, so there's no longer a potential difference that's increasing the current in that direction. Okay, so at that point, at pi divided by 2, I have some current going through the inductor. Okay, but the capacitor, so there's no longer a pressure that is forcing more current through the inductor, because this voltage reaches VI. But remember, capacitors like to sit around holding voltages. Just remember that demo. That rinky-dink capacitor sat there stubbornly holding its voltage, okay, and had a huge spark towards the end. It just sat there holding its voltage. In the same manner, inductors love to sit around holding a current. Okay, they will do whatever they can to keep the current going through them. Okay, so it's got the current going through. Okay, and few forces on earth can change that. And so therefore, even though the capacitor voltage is VI and the voltage drop across the inductor is 0, it still keeps supplying a current. It's got the current, okay? It's got inertia. It keeps going. It's like a runaway train, you know. You may not be pushing the train from the back, but once it's running, it's got kinetic energy. It's going to run no matter what, at least for some more time, even if you take away the force on the train. Okay, so I've taken away the force on the punching more current through, but it's got kinetic energy. It's got current flowing through it, and so it continues to supply current. Because it continues to supply current, the capacitor voltage keeps increasing. Okay, this is a subtle insight which is absolutely spectacular. That the 0 volts across it, it still keeps pumping that current. Capacitor voltage has gone up, and guess what? The voltage on this side is higher now. Okay, but this guy is still pumping a current. Man, I've been born to do this, you know. I shall pump a current. However, because the voltage has now gone up here, okay, it's gradually the current begins to diminish. Okay, but as far as the capacitor is concerned, you pump a current into me, my voltage goes up. At some point, like a runaway train, okay, it comes to a halt. So current through the capacitor now, through the inductor now goes to 0. And the capacitor voltage reaches 2 VI. So this is at 2 VI now. Okay, and this is at VI. So now, the situation is not in equilibrium. At this point, there's 0 current through it, but guess what? I have a VI pumping in this direction now. Okay, I have the same VI punching in this direction. So guess what? Its current must now build up in this direction. Okay? Its current begins to build up in that direction. So that begins to discharge the capacitor. Okay, and the capacitor then goes down to a negative, or rather the current goes down to a maximum negative current, and this process continues. Okay, so what you're seeing here is energy is sloshing back and forth between the two, and that's kind of a key. I'll just quickly put up a demo that you can watch as you're walking out. So for a step input, notice the green is the voltage across the capacitor, and the orange is the current through the capacitor.